Hello, this is an IMS introductory talk on 100 to 300 gigahertz wireless, transistors, integrated circuits, and systems. I'm Mark Rodwell at the University of California, Santa Barbara. I'd like to acknowledge my co-authors. Why are we interested in 100 to 300 gigahertz wireless? And the answer is potential for extremely high communications capacity. The first reason is between 100 and 300 gigahertz, there's an extremely large available bandwidth, and hence that directly allows us to maintain very high data transmission range if we are allocated that large bandwidth. Secondly, if we use that large bandwidth in phased array transmitters or receivers in the right architecture, we can radiate as many independent signal beams carrying independent different information as the number of elements in the array. And this allows us to use the spectrum over and over again and further greatly increase the communication capacity. Of course, we can do that either at low frequencies or at high frequencies, but it's easier to do it at high frequencies because the necessary element spacing is half a wavelength. And so at a high frequency, such a array with many elements is still physically compact. With these two factors in combination, the aggregate communication capacity can be in the many hundreds of gigabits per second. Against these advantages, a massive disadvantage is extremely limited transmission range, probably for a terrestrial system in the order of half a kilometer to 1 kilometer. This is for two reasons. First, the friss or beam diffraction path loss is the ratio of received to transmitted power varies as lambda squared over r squared. And so this is a poor fraction at very high frequencies. Secondly, as we will see in a moment, under worst case conditions, the worst case atmospheric attenuation can be very high. So to build such systems, we need to produce a large ratio of received to transmitted power by building arrays with very, very many elements. We need to build receivers that are very sensitive, which is to say with low noise figures. And we need to have transmitters that have medium or moderate output powers and high efficiencies. In building these high frequency systems, we have a number of challenges. Again, as I mentioned a moment ago, the ratio of received to transmitted power varies even in good weather conditions as the ratio of wavelength to propagation distance squared. And we need to offset that large propagation losses by using arrays in the receiver and transmitter, having many elements in the transmitter and many elements in the receiver. Even beyond this, the atmospheric attenuation under worst case conditions can be very, very high. Typically in a commercial communication system, we need probabilities of loss of service in the range of 10 to the minus 4 to 10 to the minus 5, so as to maintain customer satisfaction. At the range of 10 to the minus 4 to 10 to the minus 5 probability, over most of the frequency range, the dominant problem is rain, which can be as large as 50 to 100 millimeters per hour. Even at 50 millimeters per hour, at 50 gigahertz, that's giving us 20 dB per kilometer rain attenuation, though it is decreasing roughly as frequency to the fourth power at lower frequencies. Above roughly 250 gigahertz, the dominant source of atmospheric attenuation in the worst case, surprisingly, is not rain, but simply molecular absorption due to high humidity. If we're dealing with temperatures on the order of 35 Celsius at roughly 90% humidity, this becomes the dominant source of attenuation above 250 gigahertz. The final problem is high frequency signals are easily blocked because the first Fresnel zone, which is the area where most of the radio signal energy is carried between the transmitter and receiver, has an area of approximately the product of the wavelength and the propagation distance. So again, an object that covers this area will block the beam. And so in high frequency systems, we either need to ensure that the signal path is out of the way of possible objects that might block the beam, or we need to provide multiple redundant signal paths. So building on these systems, here's a couple of concept systems which we might consider using these. The first is a wireless hub at 140 gigahertz, which is communicating to 64 end users, each getting 10 gigabits per second. We will communicate with those end users using an array of 128 elements. We will design the system for about 70 meters range, which is about 2 city blocks. And we'll make sure that it works in under extreme 10 to the minus 4 probability weather, which is to say 50 millimeters per hour of rain. We will design the system conservatively and give ourselves 17 dB of margins against things like equipment aging, manufacturing variations, and partial beam blockage. If we assume that the handset and the receiver is an 8x8 array, which is about 1 square centimeter, and if we assume that the receiver has about an 8 dB noise figure, then we compute the link budget with these above parameters. We can conclude that each element in the transmitter needs to radiate about 100 milliwatts. Now, neither the 8 dB noise figure nor the 100 milliwatts output power is particularly challenging at 140 gigahertz. These have been demonstrated in numerous publications. It is simply a question of what is the cost of building a system, and is there a significant market application that would be that would justify that cost. So we'll discuss this in greater detail as the talk progresses. Here is a second concept system, in this case, no longer the endpoint link to the mobile user, but a wireless backhaul link to the internet backbone, where we're going from one telephone pole to the next. Let's assume that on each telephone pole we have 8 transmitters. On the subsequent one we have 8 receivers. These signals are mixing as they propagate, but we will use phased array techniques, aka MIMO techniques, in the receiver to separate these signals. We will do a link budget assuming that each element in the transmitter and each element in the receiver is in fact a 16-element subarray. That will give us a bit of beam steering. It will also help the link budget. Let's assume that each of the transmitters is radiating 80 gigabits. There are 8 of them, so that's giving us 640 gigabits per second total data rate. We'll do this over half a kilometer range, again under extreme 10 to the minus 4 probabilities. We'll give ourselves conservative safety margins. Then if we do that link budget and if we assume that the receivers have 8 dB noise figure, then each element in the transmitter needs to radiate about 50 milliwatts. Once again, these numbers are well within the state of the art. So this is a second concept system, which we will work towards. A third concept system might be to help us drive in extremely unfavorable weather conditions using a automotive radar system at 210 gigahertz. There's a so-called Mills phased array system or crossed array system, which uses 2 linear arrays, 1 by n and n by 1 arrays, and that produces an image with n squared pixels. So it's a hardware efficient way of doing this. The objective is to provide a video-like image using radar so that we can see while driving under extremely inclement conditions. If we do a link budget for this 36 element transmitter to 16 element receiver, the arrays are about 6 inches long and about a 40 hertz scan rate. Doing a link budget, assuming that each element in the transmitter is radiating about 50 milliwatts, each element in the receiver has about 6 dB noise figure, we can compute that with about 200 meters range, we can see a basketball or a soccer ball that has about minus 10 dB reflectivity with a decent signal to noise ratio, even under extremely high fog attenuation of about 20 dB per kilometer. 200 meters range corresponds to about 10 seconds warning while driving at freeway speeds. So this is another concept system. Let's look at the hardware we might use to build such systems. In building systems for 100 to 300 gigahertz, we need good high-frequency transistors. CMOS, surprisingly, has excellent output power and low noise figure up to about 150 gigahertz. Here I'm showing you graphs of receiver noise figure as a function of receiver and transmitter power added efficiency on the vertical scale, on a log scale, versus transmitter saturated output power, again on a log scale, broken down into 4 frequency bands going up progressively in frequency. What we can see is CMOS is doing pretty well up to about 140, 150 gigahertz, but performance is dropping off pretty quickly above that. If we want to work at higher frequencies than that, the silicon germanium HBT outperforms CMOS at the higher frequencies, but is not significantly better at lower frequencies than 140 gigahertz. The gallium nitride field effect transistor is producing record levels of output power and pretty decent receiver noise figure at frequencies below 100 gigahertz. The receiver noise with gallium nitride HEMTs remains excellent up to about 200 gigahertz. But the gallium nitride is proving not at present to be a competitive technology at the higher frequencies, although several groups worldwide are working on this. The indium phosphide HBT is producing record levels of output power and power added efficiency, pretty much any frequency above 110 gigahertz. The indium gallium arsenide channel field effect transistors are providing record low noise figure at almost any frequency of consideration. Let's look at a bit more detail at the high frequency transistors. In indium phosphide, the best field effect transistors are produced by Northrop Grumman. Record results demonstrated in 2016 with a 1.5 terahertz power gain cutoff frequency, and they've built amplifiers to 1.0 terahertz. Teledyne in the 130 nanometer node is building indium phosphide bipolar transistors with 1.1 terahertz power gain cutoff frequency and about a 3.5 volt breakdown, and they've built amplifiers to about 670 gigahertz with this. If we drop down from the 130 nanometer node to the less expensive 250 nanometer nodes, the power gain cutoff frequencies drop, but you get a bit more breakdown voltage. This turns out to be an excellent technology for power amplifiers between about 100 to 200 gigahertz. What would we need to do if we wanted to build still higher frequency systems with excellent performance? We would need transistors with further improvements in the power gain cutoff frequencies. To do this, we follow scaling laws, which are simply each doubling in bandwidth of the bipolar transistor requires approximately a 4-to-1 reduction in the lithographic feature sizes. Each doubling of the bandwidth requires that we make the semiconductor layers about twice as thin. These principles are fairly straightforward, but two other key points are we must increase the current density in the transistor 4-to-1 each time we double the bandwidth, and we must reduce the resistance per unit area of our metal to semiconductor ohmic contacts roughly by a factor of 4 each time we double the bandwidth. As I have mentioned on the previous slide, at the 130 nanometer node, Teledyne's transistors have about a 1.1 terahertz Fmax. My group has done a lot of fundamental work to the subsequent 65 nanometer node, which in principle should give an Fmax of about 1.5 terahertz. We've got all of these parameters here, but we haven't yet demonstrated a 1.8 terahertz device. I simply state this to say that at the point where this becomes relevant, a wider bandwidth transistor is feasible. In looking at similarly increasing the bandwidth of field effect transistors, the principles again are similar. Each doubling in bandwidth demands that we reduce the gate length by a factor of 2. We must also reduce by a factor of 2 either the thickness of the gate dielectric, or we must double the dielectric constant of the gate dielectric, one or the other. We must reduce the resistivities of the ohmic contacts to the source and drain in addition. One subtle point, which is difficult to explain with very limited time, is we must increase what's called the state density of the semiconductor channel. This is the number of quantum states available to populate with electrons, and is necessary to increase the current density as we go through successive scaling generations. As I've mentioned, the Northrop Grumman team has a 1.5 terahertz Fmax. My group has developed transistors where we've addressed one of those scaling limits, the gate insulator scaling limit, by replacing the semiconductor barrier with a high K gate dielectric ZrO2. And we've obtained decent, though not state-of-the-art, results doing this. I caution you that the path to further bandwidth improvements in the InGaAs field effect transistors is somewhat unclear because this is a necessary but not a sufficient improvement. We also need to address the issue of state density in the channel, and this might possibly, but not for certainly clear, be addressed by replacing the indium gallium arsenide channel with a channel that has somewhat larger carrier effective mass like indium phosphide. As we move from the transistor work to the circuit work, on a system level, what we need is transistors transmitters with high power added efficiency and high power density, the amount of output power per unit gate width or emitter length. On the receiver, we need low overall noise, but because the gain per stage is low, it's important to understand that the overall noise is not simply the noise figure of the first stage, but the noise figure of the second stage divided by the gain of the first stage, and so on. Also working at high frequencies near the transistor cutoff frequencies, the gain per stage are necessarily low, so we need to use many stages to get the necessary gain. That certainly burns up a lot of die area and DC power, but also gives us accumulated gain compression, and this is a design challenge. So what can we do about that? Our gain per stage is low because we're working at a significant fraction of the transistor cutoff frequencies. It's really critical to understand that although because of this challenge, there's been a tremendous amount of work on enhancing the gain per stage of microwave and millimeter wave circuits using tricks like neutralization or Singh-Hacker-Winter's unconditionally stable positive feedback, that although we can increase the gain per stage, what we can't do is improve the fundamental noise performance or the fundamental output power and efficiency of the transistors themselves. These are bounded by fundamental limits. House and Adler showed back in 1958 that the cascaded noise figure that I mentioned is a so-called network invariant. Embedding the transistor in a lossless circuit, no matter how clever, does not improve the circuit noise performance beyond the fundamental limit of the transistor. It's equally simple to show a similar relationship for power amplifiers, that a graph of power added efficiency versus added power, output power, take away input power, cannot be improved by embedding the transistor in a lossless passive network. So the best we can do as circuit designers is pick a topology that minimizes the passive element losses so that the noise figure of a low noise receiver, so the output power and efficiency of a transmitter are as close as possible to the transistor fundamental limits. Now let's look quickly at a few high frequency integrated circuits. Here is a approximately half watt power amplifier at 150 gigahertz in the Teledyne 250 nanometer technology. The power added efficiency is about 15 or 16%. Here is another power amplifier, again in 250 nanometer technology, HBT technology at 220 gigahertz. The efficiency is about 18%. The output power is a little bit more than 75 milliwatts. There have been yet better results by Zach Griffith and colleague at the last IMS with up to 25% power added efficiency at 220 gigahertz. And I encourage you to track down that result. Here in the indium phosphide technology is an example of a low noise amplifier at 200 gigahertz with a noise figure in the range of about 5.5 to 6 dB. Moving from basic circuit blocks to full transceivers, here's an integrated transmitter and an integrated receiver. The transmitter takes a local oscillator reference at 25 gigahertz, multiplies it in frequency to make a 200 gigahertz local oscillator, and uses an IQ mixer to take the baseband data and bring it up to the modulated RF carrier frequency. The receiver block diagram is similar, with the signals flowing in the opposite direction. Both the transmitter and the receiver have about 20 gigahertz bandwidth, around 200 gigahertz. The transmitter produces about 16 dBm. The receiver has about 8.5 dB noise figure. Here's a similar transmitter and receiver chipset, in this case at 280 gigahertz, again in indium phosphide HBT technology. The receiver has about 10 to 12 dB noise figure. The transmitter about 13 dBm output power. One of the key challenges in high frequency systems is that of the phased arrays or MIMO arrays. So this is the millimeter wave design problem. If we're building a phased array radar for a jet plane, that radar needs to steer 180 degrees both vertically and horizontally. And to do that, we need a phased array that's two-dimensional, and the element spacing needs to be half a wavelength. Now, the higher the frequency, the shorter the wavelength. If we get up to the range of 200 to 300 gigahertz, it becomes very small. We have two problems. How do we fit the electronics into that small area? How do we get out the heat? One way of addressing that problem is to move the antenna array from being underneath above the integrated circuits to being beside it and running interconnects between that. There are two problems. One problem is the high frequency losses on those interconnects, and the other is just physically routing them as the array becomes larger. So this approach can work for perhaps a 16-element array, but is not viable for larger arrays. This two-dimensional array problem at half wavelength pitch is a fundamental high-frequency design challenge that is being addressed and worked on by many research groups in the IMS community. It is therefore critical to understand that there are many, many systems where you do not actually need to solve this problem. If we have a base station that is communicating to many mobile end users on the ground, there's no one floating up in the sky, there's no one in a hole in the ground. We can therefore steer the beam just horizontally, not vertically, and we can do that with a linear array. In a linear array, the antennas run up and down the middle of the array, and we have plenty of room on either side of the array to put the electronics and to place large heat sinks to remove the heat. In a backhaul array, we need some degree of electronic beam steering so that it's easy to install the transmitter and receiver without aiming them too precisely, and to keep it precisely aimed as the wind blows things around. But we certainly don't need 180 degrees of beam steering. And we can do a few degrees, 10 or 15 degrees of beam steering with an array where the element spacings are much larger, and hence the tight spacing issues go away. I had earlier mentioned the concept of doing two-dimensional radar imaging using crossed linear arrays, and clearly, again, the packaging challenges there are mitigated because 1D arrays are much easier than 2D arrays to realize. Let's look now at a couple of example systems to give a sense of the kind of work that is going on. Here from a number of years ago, no longer a state-of-the-art result, is a result of a collaboration between my group and Samsung Research North America in Dallas. The concept is, again, that MIMO array base station that I had mentioned at 140 gigahertz. We take the overall large array and break it into tiles. In this case, each tile has 8 elements, antennas. Those antennas are driven in this transmitter array with 8 CMOS transmitter ICs going through 8 indium phosphide power amplifiers ICs, each producing 100 milliwatts. In the demo that Samsung reported, they just went with those 8 element arrays rather than building a larger one, and they demonstrated steerable beams and data rates up to 2 gigabits per second over 120 meters. Let's move up to the higher frequency systems. I had mentioned to you the concept of backhaul links with these high frequency systems. Here was that, again, a cartoon of that 8-element MIMO backhaul array. Presently, we are working to build such a system at UCSB, although we don't have the resources to build 16-element subarrays, so there's no electronic beam steering within the array. Here are the transmitter and receiver ICs. They're the same 200 gigahertz ICs I'd shown you earlier. To radiate the signal, these are wire bonded at 200 gigahertz to arrays of patch antennas on a fused silicon substrate that radiates the signal into space, where it is collimated by Teflon lenses, setting the primary aperture gain. We're doing link demonstrations, in this case of a range of 7 meters, constrained by the size of the room. That's a short enough link that we're overloading the receiver, and we're forced to put attenuation in the beam by putting sheets of cardboard to attenuate the beam. Presently, as I'm showing you here, is a link with a 32 gigabit per second data stream using 16 QAM. We are presently now working on a 4x4 MIMO demonstration of this and hope before long to have something to show you. So what's next? In working in the 100 to 300 gigahertz range, the motivation here is massive aggregate capacities approaching even a terabit per second, both because there's a lot of bandwidth and because we can do a lot of spatial multiplexing. Inherently, these systems have short range because of the high losses due to frisk path loss and atmospheric absorption. We need to concern ourselves with beam blockage. There are a variety of IC technologies present and emerging that can address this. Presently, the near-term commercial impact is pretty low because the range is too short and the cost is too high. And presently also the capacity is presently more than commercial systems presently need. So the research, therefore, to make these systems viable is we must first demonstrate as the community is now doing, not only very high capacity links, but we must reduce the cost and the DC power consumption and work to increase the range. We need to work to demonstrate high capacity MIMO links and hubs. And at the higher frequencies where this hasn't been done yet, we need to demonstrate those half wavelength pitch phased arrays for those applications that need it to provide that electronic beam steering and high aperture gain. We must also drive up the number of element because this helps us with the link budgets, but we need to do this at low cost and low DC power consumption. So there are many groups worldwide working on such systems, and hopefully many talks at the present IMS that will be working in this general field and extending the state of the art. Thank you so much for your attention.